All right, Math 1500. This is the beginning of the last. Um, well, I don't want to say that. Uh, what we're going to do here is beginning what I call two variable statistics, and what we've done so far has all fallen under the realm of one variable statistics. And just to take you back through the class, and let's just kind of reflect on what we've done. In one variable statistics, we've essentially looked at two overarching goals. The first one was descriptive statistics, and the second was inference or inferential statistics. Descriptive statistics allows us to look at our sample data and look at pictures and look at numerical summaries. So the things that I hope you learned in this class so far is if we have one variable statistics and let's say it is quantitative, then it would be reasonable to report the descriptive statistics in terms of graphs, which are a histogram or a box plot. We would want to look at numerical summaries like the mean, the median, the standard deviation, possibly the variance, the IQR, the quartiles. We'd want to talk about outliers. And in a bridge into inference on this particular variable, we studied normal distributions and sampling distributions to get to a point where we could conduct a test of hypothesis and examine a confidence interval. So it's kind of twofold. We have a statistical research question. For example, we would like to know if I think I used this before, the mean wait time at Tim Hortons is less than 3 minutes from the time period of 8 a.m. to 10 a.m. I would go out and collect data, and I would look at my data, and let's say I have 50 measurements. I would want to look at graphs of that 50 measurements. I would want to talk about the mean, the median, the standard deviation of those 50 measurements. But the next thing I would want to do is I would want to make broader statements beyond those 50 measurements and generalize to all wait times from 8 a.m. to 10 a.m. at Tim Hortons. So I can test hypotheses, I can test claims, and I can make estimates of population values using confidence intervals at a particular percentage or a specified level of confidence. Okay? Qualitative data. What I hope you've known so far or know that we can still do descriptive statistics, they just differ. Categorical data, the graphs are pie charts and bar charts, and the numerical summaries are just counts. Typically, we do what's called a p-hat here, we've seen before. X over n, the count out of the total that has the characteristic that we're measuring. And of course, we saw normal distributions and sampling distributions for p's and p-hats. We can test claims about percentages. We can make estimations on percentages using confidence intervals. So guys, that's where what we've done so far up to one variable statistics. Many of the same principles are going to apply with two variable statistics. So let's get the ball rolling here. So guys, instead of having instead of having one variable. Okay, instead of having one variable, we have two variables, x and y, and we typically see those as an ordered pair. So let's say that x is the midterm exam score, and Y is your final exam score. So student number 1 scored an 80 on the midterm. They got their act together and scored a 92 on the final, so their ordered pair would be 80-92 for the first student. The second student scored a 72 on the midterm and a 71 on the midterm, or on the final. So we come down to the 24th student. Scored a 100 on the midterm, scored a 93 on the final. So guys, we would have what I would call N, or 24 ordered pairs. And these, again, fall in the realm of two variable statistics because we have two data entry. We have two data points on each particular subject. Now, what we may want to do here is kind of twofold. First of all, we may want to examine the relationship between X and Y. And we may want to further examine the relationship by building a linear model to, again, just further explain the relationship between our X and our Y. Well, the steps here actually turn out to be called the following. The first step that we conduct in two variable statistics is called the correlation part. And there are three parts of the correlation. We have a picture, which I'll teach you how to create one of these in your calculator, and I'll teach you how to interpret those. So we get a picture called a scatter plot. The next thing we get is we learn how to calculate something called the correlation coefficient. And then we learn how to calculate something called R squared, which is the coefficient of determination. We learn how collectively with these three things discuss, examine the relationship between X and Y. The second thing I'm going to teach you is called regression. The key component of regression is our line of best fit, our regression model. So what happens here, this line, we'll see here in a minute that we can look at a scatter plot between X and Y, and we'll learn how to find and plot our data points. We want to build the line, which we call the line of best fit, because it's the line that best fits our data. We want to find the equation of the line that goes right down the central focus of our data that could be used for prediction. I got a phone call coming in. I don't know who it is, but I guess they can call me back, can't they? So this prediction, this regression equation that we find that can be used for prediction actually does two things for us. It helps us better explain the relationship between X and Y, and it can also be used for prediction. For example, let's say that this X turned out to be the ACT of a student, and Y turned out to be their first semester GPA. And let's say we're focusing just on Shawnee State University students. Well, we could see that if we have a future student coming in who has an ACT of 24, we could go up to our line that we created and get what we call over here a predicted GPA based on our model. Now, we got into something like this when we adopted our daughters from China. What they had a model that was already created, and the X value wasn't ACT. She was only 14 months, so she hadn't taken an ACT yet. But the X value was her was her height, and the Y value was her head circumference. So what they could do is they had this model, and they could put the child's height into this model and predict based on their height what the head circumference could be. The head circumference in children is really important because it gives you an idea of adequate, proper, healthy brain development. So based on Sadie's height, we determined within some confidence interval that her head circumference was exactly where it should be, and there was no evidence of any improper brain development or slow brain development or whatever that terminology would be. I'm not a medical doctor, so. But again, hers, and she's extremely bright, so we're very blessed. Now, what I want to do in this video is run through an example of the correlation part. And here are the things that I'm going to teach you in this video. First of all, we're going to have data that's going to be given. And we're going to learn how to come in and create and summarize a scatter plot. We're going to find out how to create R, the correlation coefficient. And we're going to find out how to create and calculate R squared, the coefficient of determination. We're also going to learn how to interpret these. A final thing we're going to address is our R value statistically significant? Okay, so those are going to be the four things that I'm going to teach you how to do in this video. Important video, guys. Really, if you're not able to focus, if something really cool is on TV, you're fighting with your boyfriend, your girlfriend, your husband, your wife, your best friend, your whatever, you might want to just chill out, stop the video, come back when you can focus, because this is these next two videos are pretty critical. All right, now let's talk about let's just take an example and go from there. So I'll upload this to Blackboard, so you'll have this before you watch this video. So this is a problem. Let's examine the relationship between an NFL quarterback's number of TD passes and their quarterback rating. So here's 10 quarterbacks from the 2011-2012 season. And I got this book, this data set from your textbook. First thing we have to do is we have to determine which is X and which is Y. So it's reasonable to assume that the quarterback function or quarterback rating is a function of the number of TD passes. It's very reasonable to assume that because the number of passes is used in creating the quarterback rating. So because of that, we're going to let the touchdown passes be our X and our Y be the quarterback rating. Now, gang, the first thing I would need to do is enter this into my calculator. So I don't know how I want to do this. Let me get this. Let's go screen twofold here. Really, I don't really care yet about the. All right, I'm going to bring up the calculator here and. All right, gang, so I want to just type in my data first. So I want to go to Stat. I want to go to Edit. I've got some data in L1, so I want to get rid of that. So go Clear Enter. And I've got some data in L2, and I want to clear it too. So go Clear Enter, just like we've done many, many, many times before. Now, I want to carefully type these in, so I'm going to read them off to you. It's easier. 46, 18, 27, 31, 45, 13, 17, 12, yes, I made a mistake on purpose, 29, 39. What mistake did I make? I got to 29 when I was going through. I got to 29 after the 12, so I read the 12 before the 29. I did that on purpose. I want to show you something. All right, now when I go put my data in, the value for this 46, 110.6, has to be on that line. 84.9 has to be on the line with the 18. These are ordered pairs. 27, 88.7 has to go with the 27. 31, 102.5. The 45 has a 122.5. Who was that? I'm just curious. Oh, Aaron Rodgers. That makes sense. So 122.5. Okay. 87 or 85.7. The 17 has to go with the 90.7. Here's where I made a mistake. The 12, I think that's Tim Tebow. Poor Tim. Great guy. Not the greatest NFL quarterback. The 29 has to go with the value that's on its line, the 92.9. So I made a mistake, and again, I did this on purpose just to show you that that the values have to go, the Y values have to go with the X values that we put in. All right? So, guys, we've got our stuff in our calculator, got our data in our calculator. That's cool. So I want to focus now on the scatter plot. Now, scatter plot is really easy to do in your calculator. We're going to go up here to the stat plot, so hit your blue key, or it could be yellow depending on your calculator. Go up to stat plot. Guys, make sure the 2 and 3 are turned off. If they're not turned off, you could get an error. So sometimes when we haven't done stat plot for a while, sometimes it's better right now to just to go number 4, hit enter, and just turn all the plots off and start from scratch. Because it can be really frustrating if you're home and you get an error. So, and that's a source of an error. Okay, so I want to turn it on first. Now, the very first plot that we get is the one we need, so I'm going to hit enter. And then I've got to come down till where I put my X list and my Y list. Well, I put mine in L1 and L2. You probably did too. Now, for reasons I really don't understand, If I try to go zoom stat now, I'll get an error or I'll get an annoying. So I have to go back up to the top before I hit zoom stat, which is zoom 9. Now, I've got a nice scatter plot here. But before we get into describing the scatter plot, let's get back over here and let me give you some kind of rules. Okay. Now, first thing we do with the describing scatter plots, you guys probably get tired of looking at my arm, don't you? I'm working on actually getting a on-screen device where I can teach with it. Actually shows me while I teach, but it's $100, and I'm not really sure I want to spend $100 on it. But because this works, and trust me, I'm nothing to look at. So, but I think it would just make it a little bit more personable. Now, describing scatter plots, the first thing we want to examine is our relationship linear? Well, guys, if we look at a relationship between x and y, and all the points fall on a line that we could perceive going down through the central focus, then yes, we have a linear relationship. If we have points that look something like this, and the line that seems to fit the data best isn't a straight line, then we do not have a linear relationship. All right? Now, for those relationships that we find out are linear, we'd like to talk about those whether they're positive or negative. Guys, this is easy. Lines, data, tendencies that go rise to the right are a positive relationship. So as our x values get bigger, our y values get bigger. For example, if I choose a small x, its predicted y value is smaller. As I increase the x, you can see that the y values, the tendencies go up. Now, contrary to that, what if I have a relationship like this? Well, the central tendency, so to speak, of this, the pattern of scores there, as x gets bigger, the y values decrease in general. And guys, this is referred to as a negative relationship. Okay? Now, the next thing we want to be able to do is we want to be able to get into describing the magnitude of the relationship. And I like to pretty much just think about these in terms of positive and negative. So the first thing I want to look at is a strong relationship. Well, guys, a strong relationship won't have much variation in the points. If you think about a line going down through the central focus of the data points, there's not going to be much variation that way. That would be a strong positive. That would be a strong negative. Next, we want to look at a moderate relationship. Guys, moderate relationships have a little bit more spread to them. Strong, moderate positive. Moderate negative. When you think about that line going through the central focus of the data, there's a little bit more variation in each of these than you see in a strong positive or negative relationship. A weak positive relationship has even more variation. A weak negative relationship has even more variation. So again, and guys, in the end, we could get into a situation down here at the bottom where we have X and Y. Sometimes we get data points where there's no linear tendency. They're just completely scattered. This would be no relationship. All right? So when we look at our relationship between quarterback rating and where are we at here? Okay. What do we have? First of all, is it a linear relationship? Yeah, it is. All those lines are kind of on, can be seen as well described by a straight line. Is it positive or negative? Clearly positive. Is it strong, weak, or moderate? I think it's strong. Okay? So, gang, we could say, therefore, that the summary of our scatter plot well, that may be the ugliest scatter plot written now. I can't even handle that. That's just too ugly. Our scatter plot for X equal number of TDs and QB rating is linear, positive, and strong. The positive part just tells us, in general, QBs with more touchdown passes have higher QB ratings. So there's a relationship between the number of touchdowns and the quarterback rating. Guys, can you think of any relationship that would be negative? Essentially, a negative relationship tells us, as in general, as X increases, the Y values decrease. Up here, it's positive because as the quarter number of touchdowns go up, it appears there's a relationship with the quarterback rating being higher. Can you think of anything that would create a negative relationship? What about focusing on one particular car and look at miles per hour, miles per gallon? Guys, the faster you drive, the more gas it takes. So your miles per gallon goes down. So as miles per hour goes up, again, we'd have to control this on the same vehicle. The miles per gallon actually go down. Okay? All right. So you can see the scatter plots are really kind of cool, kind of really easy to create and to summarize. Next thing I want to do is I want to come in and talk to you about R and R squared. It actually turns out that with your calculator, R values are really easy to find. Once we find an R value, then R squared is literally R squared. For example, if we find an R value of 0.80, then the R squared is literally 0.80 squared. Often we report our R squareds as percentages, so it would be 64%. So guys, within the next probably 10 minutes or so, I'm going to teach you more about R and R squared than you ever cared to know. Guys, the formula for R squared, the formula for R is ugly. I'm not even sure I can remember it. That's funny. I don't remember if I remember it because I know this thing by heart. Now you're probably all fast forwarding. Yep. Okay. So lots of summations, lots of products, sample size, all that stuff. Guys, I don't know about you. I mean, I can't say I like this kind of stuff. I think this is cool. I think it'd be really cool to teach this class where we actually went through and we found the sum of these products and the product of these sums, and I think it'd be really cool. But I think that would drive most of you crazy. Luckily for you, the TI-84 in R finds correlations really, really, really easy. Okay? Now, what I'm going to do is I'm going to go to our calculator and show you how we find these values using our calculator. So guys, we've already got our information stored in the calculator. So to find R and R squared, you go to Stat, scroll all the way over to Test, and go to what's called Linear Regression T-Test. So it's LINREG T-Test. Now some of you have got this LINREG T interval. Guys, we don't use that. It's LINREG T-Test. Now the linear regression, there's other ways on your calculator to do this, and I teach it this way because this is a consistent application. This is a consistent way with all types of calculators. There are certain calculators, as some of you probably have, that if I show you the way that I would work it if I was on my calculator, you won't have that option. You'll get limited information. This one works for all calculators. So this is the reason I teach it this way. So what I do is I do the linear regression t-test, and I tell the calculator where I put my list for X and my list for Y. So L1 and L2. Come down to your frequency. Guys, this beta and rho. That's probably looks a lot like a hypothesis testing. It is. Think of beta and rho. Well, I'll get into that later. Let's keep it simple on this one. Regression equation. I want you to go ahead and do this. I want you to go to VARS. Now you got to have your cursor right there. I want you to, you only have to do this one time, so I'll be able to tell who's watching the videos and who isn't. Go to VARS, go over to Y variables, select function, and put Y1 there. That's really going to come in handy here in the next video. All right, so go calculate. And if we scroll all the way to the bottom, we're going to see R and R squared. So guys, our R value here is 0.925. And our R squared is 0.856. So your calculator, you don't have to use that big old fancy smancy formula. Your calculator gives you this. Now, typically R squared is presented as a percentage. So the R squared would be 85.6%. Now, what do these values tell you? Let's talk about R first. R has a restriction on the values it can attain. Guys, all R values, these correlation coefficients, have to have values between -1 and +1. So when you look on a number line of possible output, possible values for R, and someone comes in and tells you, I got an R value of -3, you'll say, no, you didn't. You made a mistake. It's impossible. R values must fall between there and there. Positive R values indicate a positive relationship. Negative R values indicate a negative relationship. Now, I want to come in and give you a rule of thumb for interpreting R values. So I want you to break up this line. I'm taking this -1, +1, making it bigger so we can focus on it. Let's draw this out into -0.8, -0.2, +0.2, +0.8. A decent rule of thumb, until you learn a lot more about statistics and you find it's really not, but a decent basic kind of introductory framework for deciding what this R tells you is if our R falls between -0.8 and -1, we're going to call that for now a strong negative relationship. If our R falls between -0.8 and -0.2, we'll call that a moderate relationship. Same thing up here, 0.2 to 0.8. It's going to be a moderate relationship that is positive. If we have a -0.8 to -0.2, it's a negative moderate. If we have a +0.2 to +0.8, it's a positive moderate. Up here, you should have this figured out. This is a strong positive. Anything in this range right here from -2 to +2 is a weak relationship. If it's from 0 to -0.2, it's a weak negative. If it's from 0 to +0.2, it's a weak positive. Our R value of 0.925 falls right there. So the R value substantiates, almost you could say validates, what we saw on our scatter plot. Now, let's get our scatter plots. Let's go back to those and talk about those a little bit more, okay? What kind of R values would we get with these scatter plots? Well, this would be about a 0.90. This would be a -0.90. This would be about a +0.75. This would be a -0.75. This would be about a, +0.1. This would be a -0.1. This no relationship would create a correlation coefficient equal to 0. So it gives you the connection between having a quantitative measurement, a numerical summary, this correlation coefficient, and its relationship to the scatter plot that we create to get kind of a just an overview of the relationship. But the correlation coefficient gives us a numerical summary of the relationship. These two things go hand in hand. I like to see the picture, and I also like to see the R and the R squared. So the R tells us what? There is a strong and positive relationship between TD passes, number of, obviously, and quarterback rating. What's R squared tell us? Again, what's this R squared? It's called the coefficient of determination. What's the R? It's the correlation coefficient. Coefficient of determination. This tells us, this is one of the most important measures that we can get when we look at the relationship between an X and a Y. This tells us that 85.6% of the variance in our Y can be explained by the regression on X which is TD passes. So in other words, we've got a scatter plot. In the next video, I'm going to teach you how to create this model, which is called regressing Y on X. We come to a particular X. We want to come up here and we want to explain that variation at that particular point, the spread. Almost 90% of it, 85.6% of that variation can be explained by this model, by the regression on X. Another way of thinking about it is if we increase the number of passes slightly, then 85.6% of the variance in the change in Y can be explained by that. I like the regression better. I think it's clearer. It's probably not clearer now, but it's one of those things you just got to kind of tattoo to the brain. But once we get into the regression equations, which we'll do in the next video and the following video, it makes it a little bit clearer. All right, the final thing we want to know is our R statistically significant? Is it meaningful? Can we generalize from this sample to a larger population? Now, much like X bar could be used to predict mu, much like P hat could be used to predict P, this R value can be used to predict rho. This is the sample correlation coefficient. This is the correlation coefficient for this group of quarterbacks only, but there is a correlation coefficient out there that describes the relationship between for all quarterbacks, between their quarterback rating and their number of touchdown passes. If we went out and got another sample of 10 NFL quarterbacks, we wouldn't get 0.925 more than likely as the correlation. We'd get something different. We may get 0.918. And we pull out another 10, we might get 0.894. And we would ultimately create a distribution of sample correlation coefficients that work much like the distribution of sample means and the distribution of sample proportions. Back in the central limit theorem stuff. That central limit theorem stuff doesn't go away, does it? It's something that we all, well, not we all, but most students in statistics find it to be kind of hard. And they want it to go away because it's hard, but it doesn't. It just kind of lingers. All right, guys. Let me show you how this works. We clearly need to be able to find if our R is statistically significant. We need the same kind of stuff that we needed before. Remember, statistically significant means do we reject a null? Is our p-value less than our alpha? So, guys, we need the same stuff we need before. We need an H sub O and an H sub A. We need an alpha We need a test statistic. From that, we need a p-value. And we need a decision. All right, gang, let's do it. All right. So is our R statistically significant for this problem? Your null and alternative hypothesis for this problem will always be H sub O colon rho equals 0, H sub A colon rho not equal 0. This not equal to right here tells us we have a two-tailed test. Next thing we need to do is set alpha. If it's not given, use the default 0.05. The next thing we need to do is we need our test statistic. The test statistic for this type of problem is t equal Okay, so it's that nasty mess. I hope I got that right. Let's see. Yeah. All right, so our R value was trying to look back and see what it was. Okay, 0.925. So we need 0.925, the square root of 1 minus 0.925 squared over n minus 2. Now guys, if we go back to our data set, we can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 quarterbacks. So we need to divide that out by 8. So guys, I'm going to show you how I would do this in the calculator. What I would do is I would take care of the numerator first. So I would go, I would do this. I would go 1 minus 0.925 squared divided by 8. So I would do this in bits and pieces. So now what I've done right now is I've done this part right here. Now I know I got to take the square root of that. Now I have everything in the denominator. Now I know I need to take the 0.925 and divide by that value. No rounding off, because if I round off, I'm going to get an approximate answer. So my test statistic is 6.886. Now what I do to calculate the p-value is I use the stuff that I taught you in earlier videos. The distribution that we use here is always degrees of freedom equals n minus 2. So however many data points you have, that's the degrees of freedom minus 2. Okay? So our distribution we're going to use has degrees of freedom 8. Two-tail, we're going to look at the area to the right of 6.886. And to the left of negative 6.886. Guys, we don't need to do both of them. Let's just do this one and multiply it by 2. So t distribution, so we do t CDF instead of normal CDF. 6.886, that is right, yeah. Up to infinity with degrees of freedom, 8. I got to multiply by 2. I've got to keep in mind that, as we saw in a previous video, p-values are probabilities, so they have to be between 0 and 1. So I have to look for the scientific notation, which tells me I move my decimal place 4 places to the left, or fill in with 1 less than at zeros, fill in with 3 zeros. So my p-value here is 0.0013. Is that less than my alpha? Yes. So I reject. And I have statistical significance. My R value is statistically significant. All right, let's work a problem like what you're going to have on Hawks. Let me see if I can find. I wrote one down earlier that I wanted to work with you, but I have misplaced it. Well, shoot. Shoot. Because I had it written down here. And I can't find it. I'll tell you what, let me grab the textbook. I know the problem I wanted to work for you. If I can find it, which I know I can. Okay, here it is. Determine if R is statistically significant. And you're given the following information. R is 0.731. Alpha is 0.01. And your sample size is 11. So that's the problem I wanted to work for you. So what do we got to do? We got to create our test statistic, our p-value, compare our p-value to 0.01. If it's less than 0.01, we have statistical significance. If it's not, we don't. So guys, the first thing I want to do is create the test statistic. So I have 0.731 over 1 minus 0.731 squared over n minus 2. N is 11. We should be able to do the mental arithmetic that we have 9. The trick to it is putting it in your calculator correctly. So I'm going to just go 1 minus 0.731 squared. I'm going to divide that by 9. And now I'm going to take the square root of that. So that's my entire denominator. I want to take the 0.731 and divide by that answer. And I get 3.21. Now, I'm going to use what I know before. Find the area above 3.21. Area to the left of negative 3.21. So all I need to do is find one of these, multiply by 2. All right, so I have 3.21 up to infinity. Degrees of freedom, 10. No, wait a minute. Degrees of freedom. I'm wrong on that. I'm working degrees of freedom are n minus 2, right? Yeah. So we had 11 instead of 10. Okay, so degrees of freedom are 9. I need to multiply that by 2. So the p-value is 0.0106. Well, gang, 0.0106 is actually greater than 0.01. So at the alpha level of 0.01, it is not statistically significant. So guys, you got a gambit of information here. You got an information of how to look at a scatter plot, how to summarize a scatter plot, the connection between a scatter plot and R, how to find R, how to find R squared, how to interpret those, and how to determine if R is statistically significant. Okay, so if there's significant information that R is not equal to 0. All right, gang, that's it. Take care.